So, yet another overview of GNSS, the classical one. We have satellites and ground stations, which track the satellites, and then we determine the constants of motion, orbital parameters from that. And, well, this is how the usual positioning works. But if we put inter-satellite links to the satellites, then we have a lot of information, many proper times of all the satellites coming and going and everything. So maybe it could be possible to use all this information to get rid of the ground stations, do some bad analysis and data reduction and everything, and get to the same result. So, and this idea we tested for the first time during the Ariadna study. It was a really much simpler project. We had a spherically symmetric Earth, no perturbations, nothing. Then, of course, because of that, we got some degeneracies we couldn't get rid of, but as we will see now, the perturbations actually help us to get rid of those. Okay, so how did we do it? Okay, we have perturbations. We included Earth multipoles up to the 6. Ocean tides, solid tides, Moon, Sun, Jupiter, and Venus. Relativity is typically done by hand when you're doing Newtonian concept, but with our method, it was already there. So the Newtonian concept is you have accelerations, you just sum all of them for each perturbation, and then you let the simulation run. But in general relativity, we work with metrics, and we chose to start not in flat space-time, but in Schwarzschild, which is the next better approximation of the space-time around Earth. And we added perturbative metrics to the Schwarzschild one. We use the Reggie-Wheelers-Lilly multipole expansion also for the planets, not just the shape of the Earth. Yes, with those, and you can see that there is no term which would be named relativity, because relativity is already included in each of them. And it's not done by hand or anything, it's just there. You don't have to worry, did I include this effect or that effect, and then, or maybe I included it twice accidentally. You don't have any such worries, because everything is there and it's super clean. So, when this was done, we needed to simulate the orbits, actually the dynamics of the satellites. We did this with Hamiltonian principle. So this is how it's done in general relativity. We have the orbital parameters, 6 of them. They are the same, just like in Newtonian case. And what we have is, for the orbit, we know the analytical expressions for the orbit equation. And this is really super fast to calculate, and let's say it's easy. It doesn't make, I mean, it's not more difficult if we did it in a Newtonian way. But if we have perturbed orbits, then we get an additional term, Hamiltonian, and the orbital parameters are no longer constant. So basically what we do is, well, we do it the usual way. We just calculate the time evolution of the orbital parameters, and when we get this, when we do this, we find the results for the orbital parameters as function of time, and then we use those results in the analytical solutions we had before. So it's like an iterative process, and it works perfectly as long as the perturbations are small enough. And in case of Galileo, they are big. So we end up with basically the same orbit equation. The only difference is that now the orbit parameters are depend on time, on proper time. Okay. So this is just one example of time evolution of the orbital parameters in case of Earth multipoles. So the semi-axis doesn't change on average. An inclination, and we get, this is for the line of nodes is the one which well, one is which what is it in English? Yeah, line of nodes, and the line of the sending node, and the other one, longitude of the periapsis, I think. Yeah. So and they move, they evolve in the same way as in classical case. We checked this also for different inclinations, and the results agree. So at least we can be sure that our mathematics is okay. No? And this is, I'm not going into more details because to get to those, it's really no way. It's so many equations and everything. So, okay, this made me more interesting. We wanted to see how the perturbations affect the position of the satellites. So what we did is we simulated the satellites, and we included only one of the perturbations. And then we compared the position of the satellite on a perturbed orbit and on unperturbed orbit, so on pure Schwarzschild. So actually when I say unperturbed orbit, actually it would be, in Newtonian terms, it would be classical orbit plus relativity. So whenever I say unperturbed, the relativity is already included there. Okay, so we calculated the differences, and this is what we get. So we can see that if we don't include the quadrupole, then after 1 year of integration, the difference in position can rise as much as 10,000 kilometers in 1 year. Okay, but this is not the this is the difference actually along the orbit. So this is 10,000 kilometers of along the orbit. And for the smaller perturbations, of course, the difference gets really low. And the smallest one is, of course, the Kerr effect. So this is the one due to the relativistic effect due to rotating Earth. Okay, this is really the smallest one. And actually, while the equations are the simplest for that one, it's the numerics is much more difficult for that because it's so small that we can easily lose the effect in our calculations. Okay. Now the positioning. Andrea already said about it. I won't spend much time on that. I just want to say that if you use the relativistic approach, the general relativity equations or anything, and try to determine the position of a user on Earth, it's really not a technical problem. You can do it in, let's say, in this much time with accuracy which is ridiculous. Okay, but it's just to show you that it works. We can easily, stop our calculations sooner, so the accuracy is much more reasonable. I mean, it doesn't make sense to go to 25 digits to the size of an atom if there are many other things which can spoil the results. So, but it can be done really.
Uros,
yeah.
Just a quick one. The user only has one input in practice.
Sorry?
The user,
yeah.
which is your GNSS receiver, has only one input. That's the signal in space coming from the GNSS satellite constellation. So you have here two inputs. One is what obviously comes from the satellite, and the other one is your after data reduction, correction, constants of motion, etc. You arrive at what you need for the coordinate transformation. This would also have to come through the signal in space to the user.
It's either way. Either it comes, the user should either get the orbital constants or already the positions x, y, z of the satellite. Anything. So then
it would have to be, if it's processed on the ground, it would have to be brought back to the satellite.
Yes,
to go to
exactly. But see, I know which makes more sense. I mean, if you just receive the positions of the satellites, then you have to do it all the time, calculate them and everything. But if you just send the orbital constants, they do not change so quickly. Okay. So maybe you have to do it once per hour.
Part of the navigation message.
Yeah. Part of them, yes, exactly.
It would be processed on the ground, brought back to the satellite, and then the user gets the whole story, everything he needs.
It can be processed on this.
Yeah. But the signal in space will have to be slightly modified with respect to what we have now. Correct?
Yes.
So it would be a new signal in space. The signal in space that GNSS is sending out now will have to stay what it is anyway for all the legacy receivers.
Yeah.
They couldn't use that. You don't want to change it. You don't want to say throw away your billions of GPS receivers and receivers. But if I was to apply this, with a bit of delta information that you would have to process and bring back to the satellite, you could operate like this, right?
Yeah.
Am I correct understanding?
Yes. Okay.
Because you need to send the position, the satellite position.
Yes.
With your signal. That's
what you need.
The delta. No?
Exactly. That's the new thing you need, which you don't have.
It's pure geometry, you know. You need to know
so you would
locations.
still send your timing signal exactly as you do it now, but you would also send your attached orbital parameters.
Sorry, but I think the idea also is if the satellite is sending not the constant of motion, but like the inter-satellite, also the inter-satellite observables.
Yes, but if it sends...
The receiver could do the calculation, no?
No, there's no
the problem is, I think the point that is
up
made
to a
here,
certain extent.
No, if you want to extract the orbital elements from the inter-satellite...
we need all of them.
Not all of them. No. Just two satellites, pairs. Yes, but to get the calculations, you won't do it on there, on the receiver.
First of all, I think
Up to some extent.
No, forget it.
You have two problems. One is the amount of calculation power you need in the receiver.
Exactly.
And the second is the bandwidth you need from the satellite to the ground.
Yes.
This data reduction is quite important, and you don't want to do it.
The data reduction of inter-satellite links is massive. It's huge. It takes a long time. It requires a lot of computing power.
So it cannot be done on board.
No, I would love to do it on board. Have a space, a cluster, or anything. I'm afraid not.
Current stable technology.
Yeah, exactly. No, I think it would be better to do it on ground, have a special facility with all the computing power and everything, and then just send the result back.
Was it better to get information from different pairs of satellites?
No, I don't think so. No, the result can be sent over the yes signal. I don't know.
That's how it's done anyway. And this doesn't need to be done in real time. You do this.
It's slow moving.
Yes, slow moving changes. So.
No, the ground station. I mean, you can just send this to one satellite and then spread the results.
Just the hardware for the calculation and everything.
Yes,
So it's quick.
I agree. It would be so much nicer to have all the processing done on board, because then you have a much more robust system.
You can send up an additional thing, and we're going to just do the processing there. Personal. It's nice, but it's not.
Good luck with that.
Okay. Now to the ABC system, what it is, how it works. So this is the part when we get rid of the ground stations and find all the information through the inter-satellite links. Okay, we have, this is just an example of two satellites. These are their world lines, and they communicate through inter-satellite link. So this is the path of the signal. And one satellite, I said, the satellite emits signal at one proper time, tau, and the other one receives it at tau bar. So from those proper times, we can calculate the coordinate time, which we don't know what it is. It's just some coordinate which really doesn't, it's not physically measurable or anything. It's just something which helps us to label things in space-time. But then the difference of those two times has to be equal to the travel time of the signal. And this works okay when we know exactly what are the orbital parameters, if we can reconstruct the orbit of the satellites. So what happens? Okay, so now we have satellites, and they can exchange the information continuously or at certain periods. It doesn't have really to be continuously, maybe once every half an hour or whatever. It doesn't really matter. And what we basically do is to say, okay, if we don't know the orbital parameters, we just guess, then what will happen? That the difference between those times will not be equal to the time of flight. Yes? And we just sum all the differences into one big, huge, fat function called action, marked with S. And in ideal case, it goes to 0. Yes, if we have the orbital parameters, the correct values of the orbital parameters. If we don't, then the action grows to something. So basically what has to be done is to minimize this function with respect to the initial values of the orbital parameters. Yeah? We don't have to guess what is the value of, I don't know, eccentricity here. We just need to know the initial one. And because of the known dynamics, because we have all the perturbations and everything, we can calculate the evolution from the initial condition. So all we need is, for example, 12 different parameters, 6 for each of the satellites. Only their initial values. So we end up with minimizing 12-dimensional function. And this is one example. This is an example with all perturbations included, from quadrupole to Kerr effect. So from the biggest to the smallest one. And we did it in 2 steps because, well, it turned out, of course, we need to use high precision numerics if we don't want to lose the smallest perturbations. But if we do it from the very beginning, well, when you do the high precision computations, it takes really a long time to do it. So we split the problem in 2 pieces. First, we do it within our precision, go somewhere, and then actually we already get very far. So these are the parameters. They're scaled from 0 to 1, and their true values are at 0.5. Okay. So what happens? We have parameters scattered, well, all over the interval. And as the minimization progresses, we see that they slowly converge to their true values. Okay, it's already 0.5, but we don't know how many digits we have, right? And we see the minimization of, this is plot of the action. It starts at 10 to the 24, whatever. It depends on the number of communication pairs. Of course, it grows with that number. And then it ends up with 10, just above 10 to the 10 in some units. Then what we did, we took the results from this minimization and used them as starting point of the next stage of the minimization, which was done in quad precision, so 128-bit floating point.
Ask you a stupid question.
Yeah.
On the red plot up there.
The previous one?
The previous one, yeah.
Yeah.
Why is this not monotonous? Why is it?
This depends on the minimization method. Yeah. We tried a number of them, and this plot is different for each of the methods. It depends on how it works, how the minimizer decides where to go, where to try the next point, and so on. That's why it's not. Okay, so we went to quad precision, took the previous results, and we can see that we got to 3 digits for, I think there are two parameters here hidden. Changed also the minimizer. This one was much more robust. And in the end, the action dropped to 10 to the minus 25, which is the limit of, already to the limit of numerical accuracy. And the accuracy of the orbital parameters was 10 to the minus 22. Again, a ridiculous number, of course, but it's just to show that it can be done. We could easily, if we stop minimization here, okay, then the end result would be, we would have a much bigger error, more reasonable one, of course, but just to show you, you can see it's 10 to the minus 22. Right? Okay, so this is really, we decide basically where to stop it. So do not exaggerate that. The degeneracies, you already spoke about that, or was it you? I don't know. In Ariadna, we had problems with degeneracies. In what way? If we have, I should use that. No. We quickly explain what the problem is. We say this is Earth, and if it's spherically symmetric, then we have 2 satellites, for example. One here and one here on this orbit, right? So when we try to determine the orbital parameters, the problem is that, let's say if we move this orbit to this, yeah, and the bottom one also like this, so that the orientation between the two remains the same. if the case is spherically symmetric, we cannot distinguish between the two. So during Ariadna, we just said, okay, we have to fix one orbit, and then we can calculate the mutual orientation of the orbit, right? But now, if we have all sorts of perturbations, just for simplicity's sake, let's say this is a quadrupole, this is the shape of the Earth now. Yeah. When we do calculations, if we just change this orbit to that one, we get different communication signal. Right? Because the shape of the Earth already tells us that we cannot move the orbits other way than that. So this is basically what we found out. This is just maybe an easier way to show you how it works. So this is without perturbations. This is the two-dimensional scan for action for inclination. So you have two orbits. And you can see that if you change both inclinations in the same way, like this, okay, you get a value which is flat and very long. Yes, and if you calculate the with Hessian matrix, the eigenvectors, you get the directions, and this is the plot along the two directions. The blue one is along the valley, and the red one is perpendicular. So you can see, if you move like this, you find the minimum of the action. Okay, but if you move along the valley, it's flat. Okay, so we have degeneracy here. Yeah. Now the same plot, if we include the multipoles and tides. You see, on the image it looks flat. It looks flat, but when you actually try the numbers, you see that you no longer have a degeneracy. Yeah. And another example is for the line of ascending node. So orbit and move it like this. Yeah. Same thing happens. You have degeneracy, and as soon as you include the perturbations, it's gone. So the perturbations are actually a good thing for ABC. What we have now, so just to make a quick summary of the ABC, what it is. We have two satellites communicated. Let's say the black one emits signal, the red one receives it. And from that alone, we can determine the orbital parameters of both of them, not just one. But we can change the roles of them. So the red one emits and the black one receives. And we will get the parameters for both of them. Yes. In ideal case, we would get identical numbers. Yes, but there are no ideal cases, so we have now two values for each parameter, and we can make an average of that. Now add another satellite, and you have 20, 30 of them. So you get many numbers for the orbital parameters. And by averaging them, you can get actually to a better value. And not just that. Let's say that maybe something goes wrong with one of the satellites. I don't know, maybe it's hit by a small meteorite, so it's still not destroyed, but it changes the orbit. Yeah. What we will see is that whenever you determine the orbital parameters of one satellite, the others will just see that whenever that particular satellite is included, you get strange results. So you can really pinpoint which one it is that's going wrong. You know? So this makes the thing stable. You know? Of course, this all works when you assume that you know the values of the perturbations. You know? So we wanted to see what happens if we don't know them. So if we say Earth multipole is something, and we modify this value, what happens then? This is again a plot of the action, and on x-axis is the first quadrupole, 2, 0, right? And here, the relative error here is 7 times 10 to the minus 5. So when you go here, the relative error just decreases. And of course, when you decrease the error of the multipole, the action goes down. Yes, and it can go down until here. What happens here is that we reach the numerical precision limit. Yeah, when you're doing it in quad precision, so 10 to the minus 31 something. Yeah. So this also tells us what is the maximum accuracy with which we can determine the multipole. No, and it's given here. No? When things start to break down, no? When you reach the numerical limit, then you cannot improve the value of the gravitational parameter anymore. Yeah, and you see that with this method you can go really, again, ridiculously accurate. No? We repeated this for basically for all the perturbations which we included, and we got this. So those are the values, the relative errors, which go here. Okay, and then we calculate what we modified the gravitational parameters, simulated the satellites, and then again calculated the difference in positions between perturbed and unperturbed orbits to get this column. So this immediately tells us if we make a mistake on gravitational parameter this big, then the position of the satellite will be wrong like this in meters. After 2 months, yes, after 2 months. That's right, forgot to say it. So the values, I think those values, the accuracies were taken not just arbitrarily. We took the accuracy with which they are known now and made it worse by 1,000 times. And even then, the difference in position of satellites is not catastrophic. So I would say if we use the current values of at least for multiples, actually also for the remaining parameters, we shouldn't worry if they are right or wrong, because I think that the Gauche thing made things really accurate. So there is no way we should worry about that. We just use those values and build ABC with it, and that's it. But it would be really a cool thing, to use GNSS to go better, because look, this is the accuracy we can get with ABC. No, yeah, of course you don't need it, but look from the numbers, So yeah, you could do it. Well, we tried it, but we ran into many problems. This is again the minimization, the action, and the parameters. We tried with including all the quadrupoles and Earth rotation. But we got only so far. You can see that, well, it starts to converge, but not for all the parameters. Also here with different methods. The action drops, but not to 10 to the minus something, as was the case before. Because the problem is when we add the more parameters we add, of course the complexity grows, of course. But also like I said, we did it in 2 steps. Double precision, then quad. If you do it in double, it quickly happens that we get translation errors and everything. Everything which is connected to the precision loss. So we couldn't go faster than that. But when we started to do it in quad precision, it would just take probably weeks to continue from here to somewhere to the better values. So at a certain point we just have to say, okay, let's stop. It's not really feasible with, at least with the equipment we had. But all the analysis we did and the results we had have really a million of examples show that there is really no reason why it shouldn't work. It's just a matter of having, maybe a more successful method. We tried gradient-based methods, non-gradient-based, but with gradient, it's nice if you have an expression for the gradient itself, but we don't have it. So we had to calculate it numerically. This takes also then additional computations of the action in nearby points. And if you do it too closely, then you already get the cancellation errors and you get meaningless results. So it's really...
Maybe you should specify what kind of hardware you use to do all the simulation.
What kind of?
Hardware.
This? Yeah, okay.
That's, I think, is an important point.
Yeah, of course, but when you don't do the minimization with gravitational parameters, when you just do it for the orbital, you can do it, you do it on this. It works.
That's what I'm saying.
Yes,
having
exactly.
Having a bigger
but the thing is,
computer.
yeah, but when you add a dimension, minimization, the problem grows really. It's not just one more parameter. No, it's it's a combination of possibilities which grows. You know. So yeah, maybe having an appropriate.
If you use a cluster, I'm sure things are going to get much.
Yes, but clusters, you profit from those only if you use probably some parallel global minimizers. Yeah, because local minimizers, I don't think there exist any parallel ones. You just have a point and drive through the shape of your function. You know? But global minimizers are already take longer time to get somewhere, and they will never be so accurate. The result, when they say, I'm done, this is it, it's usually still far away from the accuracy we want. If you want to beat the goals of accuracy, you will never reach it.
So I guess what I'm trying to make you say is that do we have an hardware problem here, or do we not?
I think that the lesson there is
it's hard.
In principle, this can be solved. It's just that
yes,
that's
exactly.
what is
the
the laptops that they used and the methods that they applied. I mean,
that's what I'm saying. I mean, to do this kind of analysis, you need probably a facility.
But that was not the main focus.
No, it wasn't. But it would be. No, how cool it would be, you know, to have it work on this. But it can't be done like this. So basically, that's it. I won't go through this. Pacom told everything, you told everything, so what are the benefits and so on and so on, you already know that. But this is the last point which really bothers me. But this is more a scientific application, I don't think. Yeah.
Can I ask one question, which is maybe a little bit of actuality? If your space system actually transmits to the users the timing signal and the orbital parameter information of the emitting satellite, in principle, you could then have orbital parameters of the emitting satellites that are completely different to the current GNSS ones. You could have them also non-circular, you could have them in different orbits.
Exactly.
You're not that restricted to the situation that we have now, where they have to be in the same circular orbits and so on, because you only receive the time signal.
Exactly.
If you add to the signal position signal, then you could in principle have your satellites a little bit wherever, as long as they cover, of course, and the user always sees a minimum amount of numbers.
They see each other and all the problems. But yes, wherever, it doesn't really. And not just that. If we want to do some scientific application of this sort, then you know that it's easier to find to measure with the smallest perturbations like Kerr effect when you leave the system untouched for a longer period of time, so that the effect can grow. You know.
For the scientific application. Yeah.
So it's better if you do not correct the orbit. You know. I hope it doesn't decay too fast. You know. So, yeah, but that's it. Yeah.
Can you come back on your table with the parameters of the refined parameters?
Yeah. This one?
Yes. Yeah. It's a great table.
What? No. Yeah, okay.
You said you took 3 orders of magnitudes
for the first 6.
For the first 6.
Yeah, and I took 3 orders of magnitude bigger the error to get to these.
Okay.
Yeah. For this, the mass of the moon, the distance to the moon is just arbitrarily 1,000 of the relative error of that, because I didn't really didn't bother to look up how accurately we know the mass of the moon or the Jupiter and everything else.
So these are the numbers. If you take, is it scaling like because if you put the real ones, the real accuracy that
yes,
you know for
it's
the
10 to the minus 5, 5,
yes.
18, 19.
Ah, okay, so it's
Yes, those two are quite. Actually, it's impossible to refine their values. If we made the plot for the.
so it's not it's not bigger. It's lower than these numbers. It's.
Oh, sorry. Yes. So no, 10 to the minus 11 and 20. So yeah. Right.
Okay, so
the true values
example,
are 1,000 times smaller than that.
Okay, so the true value, well, the true accuracy on omega is 10 to the
minus 11. Yes.
Okay.
Yes. So
then if you put 10 to the minus 11, or let's say on M2, 0.
Yes, what you get here, right?
Do you get like 1,000 times
most likely, yes.
smaller?
Because, yes, probably because where is that plot?
Okay, let's say
here.
it's the case.
This is log plot. This will tell you of what's the error in position of the satellite.
Yes.
Unfortunately, this is a log plot, so it looks like this, But we have linear plots, and it's really straight lines. So we have accuracy. Yes, but no, it depends on the steepness of the linear function. So I wouldn't dare to say anything about that. If it's 1,000 times smaller, then maybe the error. I'm not sure if it's 1,000.
But this graph already is good because if you say, let's say I have a centimeter accuracy in the range for the intersatellite links, it would be you would be at the, let's say at 10 to the minus 5 level.
If it's case, yes, but if it doesn't.
But this depends on the whole perturbation, not just that you missed one gravitational parameter or something. So this plot is not really telling you.
Yeah. The thing is, here is the Earth includes all its multiples from 2 to 6. Okay, so we would have to do the thing to show you. We did the plots, otherwise we wouldn't get those numbers to fill in the table. You can just decide which multiple to include, and then you can see what the effect is on the position.
It means that if you have a centimeter accuracy on the intersatellite links,
yes,
you can see immediately the effect. All these perturbations.
For the intersatellite link, yes. Yeah.
But I'm a bit surprised because the care is which color?
I don't think you can see it because it's. Can you see this?
Where is it, the care?
It's somewhere. Maybe I don't see it here either because I have a dark screen.
Is it smaller than 10 to the minus 5 or?
No, it's way below.
Huh?
It's below than that. The orange one is what? Where is it?
Where
I
is
have the report.
The red one is the last one.
The last one, which is not.
No, it is.
Is
It's the smallest one here.
Oh, it's this one.
Yeah.
Right.
So you already have a centimeter effect after
So if you have.
after a few 10 days. After 10 days, you have a centimeter effect due to care. Yes. But then you should have to compare two satellites, the effect on two satellites. Yeah, that's why you can see it.
Yeah.
But if you come back to the table, it's very interesting because it tells you if you can do better than Gaucher or not.
No.
No, it tells you if you
Yes,
can. Maybe you cannot, but
What with that?
this really tells you if
for the care effect.
for every parameters.
Yes.
Let's say, for example, M2.
M2.
Say you lower
Forget
by,
about
1,000 times,
Yes.
then you have
the M2 when you plotted
10 to the
this.
minus 4.
It was really a straight line like this, and only here we got maybe something. No.
Okay, so if it scales like the same, go back on the table. Like for M20, let's say for 10 to the minus 11, you would need a millimeter accuracy to do as good as good check.
Forget it.
Forget it, but we are at the centimeter. It's interesting because if you think about an inter-satellite link centimeter, okay, but if you think about putting only on 2 GNSS satellites, you can think about an optical link that would maybe go to millimeter now. I know it's for scientific purpose. But you would do as good. This seems to tell that you would do as good as Gaucher with an optical link on only 2 GNSS. Well, if I'm correct.
Exactly.
So I think it's a really nice result. Because here you have the numbers.
Yeah.
So, okay, for M21 and
those are
forget
just,
But this is still assuming you can take account the non-gravitational parameters.
You don't care because if you put such good links, you put also an accelerometer. And with the accelerometer, you get the gravitational continuation.
This is also without clock noise. When you remember Ariadna results, the clock noise, what it does, it moves this knee to higher value, so it gets flat here. And then the position of knee tells you how accurately you can determine the parameters. So clock noise basically prohibits you to determine the parameters accurately.
Okay, but the clock noise is included in it's a clock noise and mean budget. Yeah, maybe you need better clocks. I'm not sure. But I think it's worth really going deeper into that, because if we can convince to put at least two
satellites,
scientific,
for scientific purposes.
And you have already almost all the design, the space segment is there.
Well, the optical link hardware, you need some.
This exists. It would be. Could it be as an add-on? I don't know. But if every piece exists, and you just have to say, okay, now we want to do a scientific Galileo satellite. I don't know. You have to check if it's better to do a dedicated mission or.
So it's a good point, because it may be easier to convince to put an instrument in 2 satellites rather than on the whole constellation.
It would become a precursor block 2, which has a few features that will not be on the series, but will be from.
This was also it was a bit the approach of GSAC, no?
Yes.
To say that.
Well, certain things like the accelerometer, you could put on all of them, because mass-wise it doesn't really do much. Processing-wise it's easy, but an optical inter-satellite link is a big burden on the mass. So it would be difficult to sell it, to have it on all satellites. Two experimental satellites that have special mission, that would be considered.
What was the mass of the optical link on AlphaSat? It didn't look, at least what you see, it didn't look overly.
No,
but AlphaSat is big, so.
The mechanics and the optics that you need, I'm pretty sure we're talking about 80 kilos or something like this. So this is sizable. It's not to be compensated by electron propulsion, the associated reduction in fuel mass. This is one of the considerations. If you go for the same platform, you could throw off some things that we have now, that you make
space for
other things.
Could you do this on geostationary or inclined geo orbits, 2 satellites there?
Anywhere. Well, higher is better because more gravitational perturbation, but anywhere actually.
Is there any more questions or comments?
Could you just go back to the table for a second? So the biggest delta L here seems to be the radius to the moon.
These are things because I don't know really how accurately we already know the distance to the moon. So maybe this is too big, probably.
But the delta L is the variation of the...
Oh, that.
Yeah, that.
But this depends on that. So if this is wrong, I mean, if this is just guessing, then this will be also guessing.
Yeah.
I think it's much better than
I hope so.
If you use laser,
yes, centimeter. Yes, I know.
It's a centimeter, even better. So it would be 10 to the minus 8.
Yeah, something like that.
Because we have all these lunar distance measurements.
Yeah, also the mass of the moon.
So,
and there are many satellites going around.
The distance to the moon is changing, so it's measured constantly?
Yes.
Is that the reflectors?
Yes, it's the reflectors.
But for
below the centimeters.
Yeah, it's really right in the middle.
Well, the thing is that if this changes, because you need a lot of averaging, you get a few photons back from this resolution, you do that for quite some time, and then you come to this precision. Okay. But if while you're doing it, things are changing, then you never.
That's true. I thought it was pretty fast to measure. No, pretty fast also in terms of time. That it was you could do it in a night.
Yeah. As I said, you keep tracking and you keep averaging.
Yeah, well, you can have an estimate which is at the centimeter with the night observation and the lunar parameter during the night, during 8 hours, let's say. Change it much. So.
No, I think that's
You only do it.
Yes.
Yeah, it takes only 1 month to go around. 8
so
hours.
it must change a lot during 1 night. More than 1 centimeter, I would guess.
The centimeter is the residuals between the ephemerides and the measurements.
So it's a process.
Any more questions? Okay, so thank you, Uros, for a very interesting talk. And thank all our speakers for coming here and actually making it such a good workshop. So.